There we go. All right. So for those coming into the recording a little later, this is our recap. It's going to run a little long. I think that's all the important things so far. All right. There we go. See, that's off to a great start. So in this class, what we've done is we've examined the design, implementation, and verification of complex systems, focusing on managing complexity at different stages of the development lifecycle, and how the development process has to be organized to deliver these systems, right? So our core topics, of course, include domain and application engineering, designing a set of reusable assets for use in not just one application, but in a variety of customized concrete applications. This is, of course, organized by thinking about a system as a series of features which fill different variation points. And we do this through the process of feature modeling and model analysis to make sure that our feature models are correct. We then design the system as a modular collection of assets which are brought together as part of a framework using different techniques for composition of a system, using preprocessors, using design patterns, and in general, using different language and tool-based mechanisms to build a system out of a collection of largely independent parts webbed together, right? And once we have this together, we of course have to test it. And we focused on different techniques for how you pick interesting feature combinations and focus your testing on the interaction of those individual features after you've taken each of the individual pieces of code and features and tested those in isolation, right? So we're going to summarize the material we've covered today. This is a great chance to ask questions and get clarifications. So feel free to throw your questions into the chat. And as we see them, we're going to answer them, right? Happy to spend some time today handling anything that's still confusing that we've glossed over before. Now, of course, this is leading to some extent into the individual assignment, which will come on January 13th, right? We've talked about this here and there. There was some more information earlier this week in an announcement on Canvas, but this is essentially going to be a take-home exam. It's going to be a set of open-ended and multiple choice questions on the course content. The idea is that this is something you can complete within about 4 hours, within about that normal exam time frame, but you'll have a longer period over the day in case you have another exam that you have to do that day. But in any case, this is going to be designed as something that you can complete within a normal exam time frame and is structured basically as an exam, but you'll turn it in as an assignment on Canvas. You don't need to sign up for it in LADOC. You just do the assignment on January 13th. If there's an issue that will prevent you from taking it that day, tell us as soon as possible so we can arrange alternatives, right? But the idea is this is based a little more on theoretical content than the assignments have been, but it will overlap to some extent as well with the assignments. All right, so let's launch into it. Over time, the scope of software has expanded, right? Our society depends on complex software now, and software expands how we've automated our factories, how we move transportation, how we conduct business, and how we regulate our bodies. All of these different domains boast software systems of incredible complexity, and many of these are long living and exist in different variants. However, growth in scope means growth in the size and complexity of the code base, and these systems have thousands, if not millions, of lines of code spread over hundreds of classes, and they just keep growing, right? And we want to reuse that code, or elements of it anyway. And we want to extend that code. We want to run it on many different hardware platforms and in many different applications or different versions of the same application with only minor adaptations. And we want these systems to last for years and years to come, right? So what does complexity mean? Well, complexity, in general, complexity can describe anything that's difficult, anything that has a lot of moving parts. Almost any piece of software you'll ever build in a professional setting is going to be complex. Anything you build in a large team, anything that's sold commercially, more or less, right? So arguably, every class you've ever taken has been prepped for building a complex system. And so in this class, what we focused on as the meaning of complexity are really two things on variability and evolution. Variability is our ability to change and customize the software. It's our ability to choose from a set of options to configure and evolve systems to the needs of new groups of users over time, and delivering these customized variants to the users that need them. Variability is not a one and done design choice. It's a conscious process of designing a system to change over time and to be changeable while still remaining understandable and still working. It requires designing and redesigning systems to be reused and to work with the code that you're reusing from other projects and working with external systems that it needs to work with. It requires a constant focus on changeability and maintainability over time. Our ability to add new options and features to the code over time, and our ability to keep the existing code still working in the face of constant change is the mark of a well-managed complex system. And much of our focus then has been specifically on software product lines, which are highly configurable families of systems built around common modularized features. So together, product lines address the needs of a particular market segment or a particular domain focus. They're developed from a common set of core assets in a planned manner. And by developing large systems in this way, following these practices, companies can produce a set of products more economically, since the development effort's been put into shared assets, and that doesn't need to be duplicated. Software product lines help companies better address customization to meet specific needs of individual customers. And this allows having a fast rate of innovation, meeting a lot of different stakeholders' needs while keeping guaranteed levels of overall system performance and quality, because you can tune the system to different needs, right? And just plug in those differences over time. Software product lines are seen in all sorts of different domains. Right. The Android operating system is a product line. It's an evolving ecosystem where you can plug in different assets to these marked points to respond to different kinds of tasks in a system, like sending emails, opening images, playing music files, right? All the way down to HP's printer firmware, to the vehicles you buy are developed as software product lines. And these are highly challenging to develop because they have different technical process, organization, and business related aspects to them beyond what a normal software system would have. The central idea of product lines is that instead of developing your system from scratch, when you need to develop a new system for a customer, instead the system should be constructed from reusable parts. Instead of composing a system always in the same manner, it should be tailored to the requirements of the customer, and where customers can select from a large space of different configuration options. The product line approach is a form of mass customization from constructing individual solutions based on a portfolio of reusable assets, where an asset can be a code component, it can be APIs, it can be UI elements, images, any other resources that you have built to plug into one concrete system or more. Right. This introduces individualism into software production, but still allows the benefits of mass production in this huge domain and the market segments that can be served. It avoids exponential explosion in time and space that we see when we attempt to take existing code and customize it for each customer. And because we're not managing entire system clones tied to tiny market segments, but rather we have one portfolio of assets and then variation points those assets plug into, right? Product lines are a feature-oriented approach, ideally based on the set of reusable parts. A manufacturer software can generate a concrete product based on the requirements of a certain customer automatically using these existing assets and some glue code. The concept of a feature is central to achieve this level of automation, and features are used to distinguish the products of a product line from one another. For example, one text editor might provide spell checking, while another doesn't, right? One provides different page stylings that others doesn't have. In a database system, one variant might have multi-user support, while another variant lacks that. One email client might support both the IMAP and POP3 protocols, whereas the second client only supports POP3, and so on. And as a result, we tend to organize and structure the whole product line process as well as its artifacts involved in terms of features that they offer and reason about the variability between them, and discussing how we control, implement, and verify those interactions between features. That way, it's easy to trace the requirements of a customer to the software that provides that functionality, right? By matching those requirements to the features and reasoning about the software as a collection of features glued together. We we make features explicit in our requirements and our design, our code, our testing, and so on across the entire life cycle. Right? So our first core topic that we move into then are domain engineering and how we model features. And for that, I'm going to go ahead and stop sharing my screen and turn this over to Sam to present.
All right. Let me start. Do you see the slides?
Yes.
Excellent. Let me just expand on it. Hi, everybody. Today, I'm going to go quick over around 4 lectures, but try to focus on the exam more than just to repeat the material. I would just review this as a student and explain to you how to be prepared for the coming exam and what are the expectations. For the first lecture about feature modeling and domain engineering, there were at the beginning some introduction for concepts. I will go through this process. Every time we touch on a topic, I will explain that there is a reference usually, and it's not just the slide you see. And we expect you for this take-home exam to be aware of the reference, because if you don't find directly the answer, which most likely will not be there, I expect you to be able to look into the reference, and definitely you will find some answer there, because this is where the source of the material is, and it expanded the body of knowledge. You will find it in the reference itself. Mostly it would be a published paper or something like that. And also, of course, the textbook, the feature-oriented engineering, you will find it in that text also. We will point to this as we go through this. So for this first lecture, we talk about the domain and try to define the domain engineering issue, and talk also about domain modeling. As you all know by now, we are dealing with the problem space and the solution space. And the outcome of the problem space domain engineering would be mostly the feature model that you've been dealing with, like an assignment to. And then we go to the solution domain, where we develop our artifacts, reusable artifacts, and some companies call them bill of features or whatever the terminology is. The idea is to have your asset warehouse where you can use all these assets, whether they are called features or any artifacts, that you're going to use it for your configuration at the end to produce your final product. But usually when we talk about domain engineering, we are not dealing with single product. We are not dealing with a single software. We are talking about developing a feature model and a product line. This product line, of course, has a scope, because every time you think of a domain, you need to make sure that you have developed a domain that is driven by business and strategy of the company, or that we can take examples. For example, we talked about the auto industry, maybe the aeronautical industry, and we talk about so many other industries that they usually develop when they are involved in sophisticated machinery. Some companies build robots, and others, they develop a domain, and the domain, let's say like a climate control in a car or autopilot as a domain. And from there, of course, they have to produce so many versions and do the exercise, the variability points, and the commonality to produce different product lines for their different models. And this is where it's motivated from. So when we talk about domain engineering, we talk about scoping the domain. And the scoping of the domain would result in a selection of features. And this selection of features, this combination of features from your feature domain diagram is going to result in an artifacts, like we said, in the solution domain. These artifacts is your assets that you're going to use to develop your products. So artifacts would result in producing products at the end of this process. So this is, we want you to have this understanding. If you notice here, in most of the slides, we have the reference at the bottom. So if you are faced with a question related to this area, you will first know from the slide, this is the area, and you will know where the reference is. And if you have issues about reference, you can even ask us during the exam, and we have no problem telling you to consult with a reference or something that would help you find a solution. It's not like magic. Usually in take-home exams, we expect you to do little research. It's not going to be like you open a book or something and find an answer there. So in common scoping approach for the domain area, we look at the product, and these are just like terminology. The product is the end, the product line, and in the product line, you have several products that you decided that it will be part of the scope. And then you talk about the features. We talk the features is to capture the commonalities and the variability in the product, and the features also have sub-features. We talk about the scope of the feature. You don't want to have it large. You don't want to have it small. The granularity of your feature is important. And later in another lecture, we talk about feature-oriented programming, where we talked about the granularity and where is the level of the feature and how much you can go in depth in your feature model diagram. The word assets or artifacts are used a little bit loosely because they are not just features. They could be a test procedure, they could be documentation, they could be anything that would support your product line. Must be all documented there so you can produce these products in a harmony and a way that can be communicated to all stakeholders. So here we are more into looking at the feature itself, that it is part of a concern. Let's say you want to build an autopilot for a car. This is the whole concern. So you say, I want a feature that would implement safety in somehow, and then you decide on this feature and include it in your product line. So it's usually a high level requirement. We prefer it to be abstracted. We prefer it to be decoupled. We prefer. And as you see in all other lectures, we talk about features requirement. And here, for example, is also an example for your feature, what it should include, what it should not include. And it talks about good feature and poor feature. And of course, testability is a big issue. For example, implementability is a big issue. Another, traceability, decoupling, and conformity, and all these issues that relate to the feature. By now, I hope everyone is clear of what a good feature would be. Then we move because we want to use tools to develop these feature diagrams. We want to use tools to do the exercise the variability points and produce a product line. As you know, in this complex area, you don't do things manually. Therefore, comes the issue of propositional logic and ability to represent our features in the feature diagram with some algebra to enable us automate the process. And as you've seen, that feature diagrams can get really very complex, and some feature diagrams are like in these shaded grades, can be subtrees, or each of these graded box can be another feature model diagram by itself. So things can get out of hand, and this is why we resort to automation. And as you are familiar now with propositional logic, we use this to help us automate and exercise these features and develop our product line. What I see, you should be just aware of these formulas and understand their purpose, and make sure that you are able to move from the feature diagram into the propositional logic in a way that then you can program it in the feature IDE or other tools like Gears, and able to exercise variation of design and go back from feature model to your assets, whether it is a code or something else, test procedure, and back and forth, and a traceability path between problem domain and solution domain. I would assume if you have any comment or question, please interrupt me so we can handle that. Here is, for example, showing you that when you have more than two children of a feature, parent-child relationship, when you have more than two, the propositional logic the diagram, because this formula was not mentioned in the text. I just thought to put it there. You have to exercise all the combinations, because this is a relation of only one out of many, and just be aware that this is how we do it. I ended this lecture in presenting a featured research paper that was actually Dr. Torzenberger was involved in this. It's interesting, and I hope you can read it. And there is a possibility that some questions will come from there. It's just a guideline for 34 principles to produce a good practice, or let's say best practice for feature modeling. The paper called them feature modeling principles. And I presented here, not all of them, just a sample of these principles that would help you to do the feature modeling. And they divide it into groups, like, for example, here, a model organization. It talks about how much, for example, best practice to develop your feature model. When you know that you need another feature model diagram, they talk about the depth of the tree. For example, you should not go more than 8 levels, and 8 levels is a lot. And this also has to do with your ability to manage the project. If you feel your feature requires more than 6 or 7 levels, then it's better to split it into another project and develop another feature model. And it goes on in these explanations, like feature at higher level are usually more abstracted, and features at lower level, it goes all the way to the code. So in your understanding, when you look at the feature model, the upper features are more abstract, the lower features are more detailed, and so on. And it talks here in MO3 about splitting large models when you feel that your feature model is getting out of hand with thousands of features. It's really strongly recommended to split it, divide and conquer. Here, for example, it talks about the modeling organization. It talks about avoiding cross-tree constraints, as you know, this with the the decoupling principle and the separation of concerns, as we're going to say in the following lectures. So you make sure that you avoid these things because they are not good programming practice. We talked about cohesion and minimum coupling with features, and these are all in the principles. Here it talks about the modeling itself, and it talks about extracting domain knowledge. You need to communicate with the stakeholders and understand all the issues before you start your project. Focus first to identify features, variants, more than looking at commonality. This is a nice point also, because when you're trying to exercise your variability options, when you develop your product line, it says do not look at the commonality, because commonalities are a lot. It's better to look at variance, variability, where is different features and different characteristics to follow. And this is easier for you to develop a new product line than looking at commonality. If you noticed, we use the term variability a lot and we ignore the term commonality. And that's the main reason for that. In the literature, you'll see everybody's focused on variability, not commonality, to develop product lines because it's easier. And here it talks in M3 about applying bottom-up approach. If you want to start your looking at your artifacts from the solution side, moving back to the problem side, that means you look at your artifacts and do traceability backward to understand and analyze your model. And this is done a lot, and it could be starting with the code, and you have exercised something like this in your assignments. Also, at the same token, it can be top-down approach, and they say this is good for experts on domain engineering who like to look at it from the abstract side, understand the big picture first, and then go down in hierarchical decomposition to understand how is these abstract features are connected to the artifacts and to the software itself. Or sometimes you use both combination, bottom up and top down to understand your feature model. So these are principles that I would advise you to keep an eye on the paper itself, because if we ask you a question, we don't want you to say, oh, okay, this was not covered. How come you give us stuff? It's related. We cannot put everything on here, but I really would encourage you, if a question comes in this area, to consult with the reference. You will find all the details there, and you have like 10 hours for the exam. So it should be easy for you to be able to trace and understand where this question is coming from. And then you deserve it. You find it, you deserve it. You go understand it, read it, and give us a good answer on it. Okay. This would take care of the first part. I don't know if I should stop at this point or continue.
Sorry, I was muted. Go ahead and stop at this point. We'll come back for your next part.
Okay, very good. All right. It's back to you now.
Great. Let's see. All right, let's see. And looks like there's no more questions so far in the chat, but feel free to throw them out there if you have them. All right, so next, after the feature models, we talked about how you can analyze those models and analyze your code and the connections between the model and the code to make sure that the model depicts not an over-constrained situation. So a situation that where you can actually create concrete products that fulfill certain feature combinations. How we can make sure that the code of the model, or that the code itself, links back to our feature model and adequately fulfills it, and that within our code that we can we can actually use feature code, that we don't have features that are never used or never enabled that can be enabled. So quickly, I know we just went over some of the propositional logic, but just as a quick reminder, your feature diagrams can be mapped directly to propositional formulas, Boolean formulas that describe what are valid feature combinations. And this defines a formal semantics that we can use to analyze to prove our system will meet our requirements, right? So in the formula, all the feature names are propositional variables. They're either enabled or not enabled, representing the features. If a feature is not selected, it's evaluated the false. If it is, it evaluates the true. And so in our example, we have two features, P and F, where P is the parent of F, right? So when we have a mandatory feature, when you have this filled circle, right, that implies that if either of these is selected, the other must be as well. So if we select feature P, we must also select feature F, right? If it's optional, it's the empty circle. That means that if we select one, if we select P, we don't necessarily have to select F as well. We can choose to, but we don't have to. If we select F, however, we must have P. So you see this one-way arrow, that's the implication. If feature F is selected, feature P must be as well. And the mandatory, it's a two-way relationship. If F is selected, P must be. If P is selected, F must be as well. Right? That's the difference between those. When we have those fans, that means that we're selecting out of many different choices. And we have two forms of that. We have the filled fan and the open. The open fan is an alternative. This is an XOR relationship. We must, if we choose parent P as a feature, we must select exactly one of these children, right? If we have the filled fan, that means we can choose at least one. This is an OR. We can choose more than one, but we must choose at least one. So if we select feature P, we must select at least one child. We can have more, but at least one must be chosen, right? So XOR, only one, or at least one. And of course, those have the corresponding formulae for them. And this is in an abstract form right now, but this is saying that we have an OR between each of the child features, right? And that has an implication with the parents. So if at least one child is, if at least one child is chosen, we must choose the parent. If we choose the parent, we must choose at least one child. And for each pair of children, we can't choose both of them, right? Okay, if that's not clear, let me know. I'm just trying to be relatively fast since we've already talked about that a little bit, right? But this lets us define arbitrary propositional formulae between at least two features, right? There's a quick question in the chat if we'll see any. There are example exams or earlier exams. Okay. There are not earlier ones. This is the first time the course has been done in this style. What we're going to do, though, is we're going to try and put together a few sample questions ahead of time. Those aren't ready yet, but we're going to try and have ahead of time a few sample questions to try. I also recommend there's some exercises with lectures 5, 11, and 12. Those are similar in style to what we would ask. Okay. The sample questions will basically be a sample exam. I don't know how many there'll be yet. We'll try, as we're developing the rest of the exam itself. We'll also develop some extra questions and we'll put those up. They'll be the same kind of style we'll ask. I just don't know how many we'll have yet. For the actual exam, there'll probably be somewhere around maybe it's hard to tell exactly how many questions, but maybe 12 or so. But the idea is it will be completable in a 4-hour time frame like a normal exam would be. How many correct to pass? What we'll do is we'll grade it out of 100 points, right? And then on the course PM, we have a mapping of how that maps to the 3, 4, and 5. And I think it's something like, if you'll get a 3 for 6 for like 60 to 75% or something like that. 75 to 85 or something is a 4, and I forget the exact numerical mapping, but it's in the course PM. You can double check that. All right, so we have these propositional formulae, right? And in addition to the graphical structures, we can also impose general constraints, and we call these cross-tree constraints. These are implications between features located in different parts of the feature hierarchy. Okay, great. Someone posted into the chat the mapping. So 51 to 70 is a 3, 71 to 85 is a 4, 86 to 100 is a 5. Anything below that is a U or not passing. We're not going to be incredibly harsh in grading either. So don't worry too much, but do your best. Study on this. Look back at the material. We'll put up some sample questions ahead of time. Yeah, anyway, I just managed to distract myself, right? But we can impose different predicates on constraints between features located in different parts of the hierarchy, whereas the graphical structures are more about parents and their direct children. Here we can impose generic constraints between different parts of the hierarchy. So for example, we might have an embedded data management system, right? And where we store a data dictionary requires supporting the string data type to store the attribute names, right? So if we enable the feature data dictionary, we must enable the feature string. In a graph structure, the minimum spanning tree algorithm requires undirected graphs with weighted edges, right? So if we enable this feature, we must have these two other features, right? These constraints are generally over Boolean variables, right? Which are usually our features are usually included or not. But sometimes you have features that have a value. They're not just yes or no, and that is fine too, right? So for example, maybe you have something a constraint if the number of processes and a multi-threaded system is greater than or equal to 5. So we have some feature, which is the number of processes, and that has an integer value, right? So that's also possible in this type of system. Now, one question we can easily answer is whether a given feature selection is valid for a given feature model. And to that end, what we can do is we can translate the feature model into a propositional formula. In this case, we refer to that as phi, and that's just a Boolean, that's a Boolean predicate that combines all these constraints across the feature model, right? A feature selection that we've chosen, the set of features we've chosen for a model, is valid if and only if the interpretation of the formula where we assign true for every selected feature and false otherwise is a valid solution to that formula. So in other words, we go through this formula, we substitute every variable corresponding to a selected feature with true and every other variable with false. When we do this, our feature selection is valid only if the overall formula is true after we plug in true for the selected features and false for the ones we did not select. If we get a false for the formula as a whole, that means this is an illegal feature combination, that we can't have that particular combination due either to how we've defined our model or due to those cross-tree constraints, right? Now, this operation to check if a feature selection is valid is computationally very cheap. It's linear to the size of the equation. And this is something that we often apply during the requirements analysis phase of application engineering, right? So we're developing one concrete instantiation of our product line. We want to know if the set of options chosen by the user is a valid one or not. And so we'll plug this into this formula and see if it is, right? Now, when a user selects features, we can give immediate feedback whether that current selection is valid. And you see here a fairly blurry screenshot from Feature IDE, right? As if features have started to be selected, it marks down which ones are no longer available, right? For instance, if we choose directed edges, we can't choose undirected edges as well, which in turn means we can't choose that minimum spanning tree algorithm because that requires undirected and weighted edges. So for example, here we have a feature model for a graph library and its corresponding propositional formula. So in this library, the edge type feature is mandatory. So you see that actually in here. Graph library is the root, that's of course always there, and edge type. Now for edge type, we have the open fan, which means we can choose one or more of these. Or sorry, we can only choose one of these. That's the XOR. So we can choose either directed or undirected, but not both. So you see undirected or undirected and not directed and undirected, right? So we can choose directed or undirected, but not both. Weighted is an optional feature. That can be there or not, right? Algorithm is also technically an optional feature. Now, algorithm has this closed fan before it, which means we select one or more of these, right? We can choose cycle, shortest path, or MST, or more than one of these. So you see down here, cycle and shortest path, or cycle, shortest path, or MST. If we choose any of those, that means we also must choose the parent, and we must choose one of these, right? Now we have some additional cross-tree constraints. If we choose cycle, we must also choose directed, right? And if we choose minimum spanning tree, we must choose undirected and weighted. And you see those embedded in here, right? Here's the cycle implies directed. Okay, now minimum spanning tree has the open fan, so we choose exactly one of these, prim or Kruskal. If we choose either of those, we must choose minimum spanning tree. If we choose minimum spanning tree, we must choose exactly one of those. So you get this formula out of the graph. Now we can take then feature selections and plug them in and see if those are valid. So let's say we've chosen graph library, edge type, and directed, and then everything else we're ignoring. So what we'll do is we'll take this formula and plug in true for each of those three and false for everything else, right? So to see if this is a valid selection, we make that substitution. Well, does this work? Well, when we make that substitution, here's what we get, right? So you see mapping here, graph library is true, edge type true, directed or undirected. Well, we've chosen directed, so that's true. and not directed and undirected. Well, we've only chosen one, right? So not false, so true, great. And cycle or shortest path or MST is equivalent to algorithm. Well, we have chosen false for everything, right? So that actually all works out. That's fine. We have not chosen cycle, so that's not really a problem, right? So anyway, we plug all these in, and now we can see if this is a valid feature selection. Well, when we solve the formula, it is. It's great. This all evaluates to true, right? So you can see true and true and true, and, well, not false is true, and so on, right? But we could try a different one instead. If we wanted, we could try graph library, edge type directed and undirected. All right, so there's going to be a problem here. You can already imagine just by looking at this equation, and you see here this directed or undirected and not directed and undirected. Well, if we choose both of those, right, that's going to be a problem. Directed and undirected will be true, which will be falsified with the not, making this entire equation false. Right, so when we plug it in, we've got this, we've violated a constraint already, and this is not a valid feature selection. So again, the idea here is that you translate the model and its cross-tree constraints into a Boolean formula, and then when you pose different feature selections, you can plug those into the formula and get back a solution as to whether this is a valid feature selection or not. This is pretty easy to check. This is something that you can also do partially as you start to choose individual options. It's fairly easy then to look at what's left and see what kind of constraints that imposes on your remaining choices, blacking out the invalid selections, as feature ID also does. Right? Now, the next question we want to attempt to answer is whether there's any valid feature selection for a given model. And so what we can do is we can take our model and we say a feature model is consistent if it has at least one valid feature selection. Otherwise, it's inconsistent, right? In a model with a whole lot of cross-tree constraints, this question is not necessarily trivial to answer whether there's any valid selection for it. If we get a big model, and if we have a lot of constraints, it gets harder and harder to identify the set of valid selections, right? And often you accidentally add contradictory constraints as your model grows and as your set of cross-tree constraints grows. So naively, we could automatically check all possible feature selections until we find a valid one. That doesn't necessarily scale to larger models. And as a result, determining whether a feature model is consistent, whether there's any valid selection, is actually an NP-complete problem, meaning there's no guaranteed efficient algorithm. In practice, though, what we can do is we can encode this as a question of Boolean satisfiability, transform our propositional formula into conjunctive normal form, where we have clauses, right, connected with and within that clause, we only use or. We can feed this into a SAT solver, and the SAT solver can apply a set of efficient algorithms to prune the state space and come back and tell you, hey, yes, there is a valid constraint, valid set of features to be chosen that meets this model, or there are no valid feature selections. Right, so modern SAT solvers can solve many of these problems with great efficiency. And what they'll do is they'll output either the first valid feature selection they find, so as a solution to the formula, and some of them can even enumerate until they try every combination and tell you all of the possible combinations or feature combinations that meet the model, right? Which lets you avoid dead ends. Are there any questions on this? Everyone's still good so far? So what we're going to do is we're going to go ahead and take a 15-minute break. Let's come back at 2:15, and we'll go over the next part of this. And in the meantime, feel free to throw any questions into the chat. And when we return at 2:15, I can go ahead and answer those then. All right, let's get back into it. There was one question during the break about whether you would need to use a SAT solver on the exam, and the answer is no, you won't need to run any piece of software for this. You should know roughly what one is and some idea of how that would function in answering these kind of problems. But we're not going to ask you to actually run the solver and get an answer back just because there are a few issues with getting the piece of software to work in Windows and things like that. So just don't worry about running it, but be aware of what one is and how it is used. So next we're going to move into implementation practices and start talking about how you implement variability in the system. So to implement product lines efficiently, the underlying code has to support variability. And variability is a very general concept. So to recap a little bit, we define it specifically as the ability to derive different products from a common set of artifacts. Software design is driven by the needs of stakeholders, manifested in the features that they want from a product. Instead of serving the needs of one stakeholder by developing a product from scratch, variable software can be tailored to stakeholder requirements. There are three dimensions we consider when looking at variability implementation techniques, which are the binding time, the technology, and the representation. Right? We're going to introduce each of these and look at specific ways that we take assets and use those to produce complete customized software. So when we derive a product, we make decisions. We decide what features will be included in that product or not. And so we say that we bind a decision. Different implementation techniques will allow binding decisions at different times. And so we distinguish between compile time binding, which is also called static binding or static variability, load time binding, and runtime binding, what's called dynamic variability or dynamic binding. With an implementation technique that supports compile time binding, developers make decisions of which features to include at or before compilation. The code of deselected features is not even included in the product when we use compile time binding, which gives us a fast, lean executable that has only the requested features and nothing else. The most common example of this are preprocessors, where we use these if-def statements embedded in the code to comment out or remove features that we're not actively using before compilation time. With an implementation technique that enables load time binding, you make the decision of what to include from the command line or when the executable is started. So during compilation, the product includes all variations, includes all features, right? But when we go to run the product, that's when we decide through maybe a configuration file or through command line parameters what's actually going to be enabled while the product runs, right? This supports more flexibility than compile time binding. We can give a universal executable out, but it also can be a little bit slower and a little less secure, right? Some techniques also support runtime binding. And with runtime binding, we can actively reconfigure software and make decisions of what features to use while the program runs, right? So through a user interface, through an API, we select what features that we want and can even change that while the program is running. In addition, some implementation mechanisms support multiple binding times, right? The different binding times each have their own advantages and disadvantages. Typically, compile time binding leaves room for more optimizations. All the unnecessary code is removed from the product, which reduces our runtime overhead. It reduces our memory consumption. It reduces our execution time. However, once the product has been generated and deployed, it's not variable anymore, right? We can't change it without going back and recompiling with a different feature selection. And so the customer loses any ability to further customize the product for their needs. A product with load time variability is more flexible to reconfigure. Instead of recompiling the new product after every change, end users can just modify the command line parameters or your configuration file and restart the same executable. And then a product where your decisions are to even delay the runtime is able to react immediately without restarting and adapt its behavior, giving the ultimate flexibility. However, the mechanisms for load and runtime binding incur usually a memory or performance overhead, right? Because often you have code that's in its own separate blocks, and now they have to communicate with each other and coordinate. And you need additional code to ensure that the unselected features aren't accidentally invoked, right? And you'll have certain consistency conditions you have to check at runtime. And all this is going to incur a memory and performance overhead that is missing from compile time binding. It also can be considered a potential security threat where you're including unnecessary functionality in the shipped product, which in turn leaves more situations where an attacker could maliciously misuse your code. This can also lead to undesired feature interactions and requires much more careful testing. So there's a trade-off to be made. Technology-wise, we have two main routes we can take, classifying different product line implementations into those based on mechanisms provided by your programming language, called language-based approaches, versus those that are based on external tools that operate in your software products to derive artifacts, called tool-based approaches. A language-based approach uses the mechanisms provided by your host programming language. This is things like design patterns, parameters, class structuring, packaging, whereas tool-based approaches use external tools, things like preprocessors, build systems, version control systems to implement variability into your product. Now, you don't always draw a sharp line between language and tool-based approaches, and sometimes you even combine them, but this rough distinction is enough to help categorize different types of approaches. Now, a major goal of product line engineering is to drive a product automatically from variable code based on a user's feature selections. So product derivation involves product generation statically or dynamically. And there's two main ways to represent variability in these variation points and how products can be generated from reusable assets, what are called annotation-based and composition-based approaches. In an annotation-based approach, the code of all of your features is merged in a single code base, generally within the same classes. And annotations in the code mark which code belongs to which feature. That can be when it's tool-based, like preprocessors, that can be explicit statements in your code that say, hey, this lines 17 to 81 belong to this feature. This can be if statements within your code that say, hey, if this feature is true, run this code. Right. So in these cases, you have preprocessor statements, if statements, and what these do is they determine which code is included or executed depending on the feature selections that you've made. During product derivation, all the code that belongs to deselected features is either removed or ignored to form the final product. Annotation-based use approaches are pretty widely used in practice because they're easy to use. They're already natively supported by a lot of programming environments. However, preprocessor and parameter-based implementations also are often needlessly complex. They often mix code, which makes it harder to read. They often lack modularity. They're often harder to understand compared to the alternative, which are composition-based approaches. So composition-based approaches locate the code that belongs to a particular feature or feature combination in a dedicated unit of some kind, a separate class, a separate package, at least a separate file, maybe a separate module entirely. And during product derivation, all the units of all the selected features and the feature combinations are composed to form the final product. So, as a simple form of this, you might have features located in different classes, and you only select the classes you need at runtime, right? By integrating these different classes together or different plugins together. So the key challenge of a composition-based approach is to keep this mapping between features in your problem space and your composition units and your solution space simple, ideally a one-to-one mapping, right? This class represents this feature and none of the code of this feature is in any other class except for what's needed to connect it to the other classes. Right? If every feature has its own implementation as a composition unit, then a product generator can simply include the corresponding unit in the composition when the feature is selected. In principle, a combination of these approaches, so annotation-based and composition-based approaches, is possible, and some blending is pretty normal. For instance, if you're using design patterns to implement different features, there's some separation of features into their own classes. Right, but then you often have like if statements in the code that'll help connect them together. And that's a linking of a composition-based and an annotation-based approach. Right. But one way you can view this distinction is look at the difference in the annotation-based approaches support negative variability, so they'll remove code on demand, while composition-based approaches tend to support positive variability. You'll add composition units on demand. Some of examples of this include preprocessors, which are a compile time tool-based annotation-based approach. Right, so they're implemented using external tools. When the code is compiled, preprocessors are used to remove code from the executable. And this is annotation-based, which means you have a note in the code saying, hey, this bit of code belongs to this feature, but you're not explicitly separating the code into its own distinct units generally. Parameter-based approaches are activated at load or runtime, so that's notes within the code saying, hey, often an if statement. If this feature is selected, run this block of code. It's language-based, meaning it uses the programming language, and it's annotation-based, which means you are leaving these notes to say this code belongs to this feature, just in the code rather than using an external tool to remove code. Design patterns are also load or runtime. They determine which features are included when the program is running or when it's executed. They're language-based, so they're based on the programming language itself, and they're composition-based, right? So you try and separate out the features in a slightly more distinct manner and then bring them together. And to talk about these a little bit more, a preprocessor is a tool that manipulates the source code before compilation with the goal of optimizing your final executable in some form, whether for speed or, in our case, to configure the executable for a particular use. The most common of these is CPP, or the C preprocessor, which is used in almost every C and C++ project in some form. It provides directives to inline files, to define macros, to remove code fragments based on user-defined conditions. But in addition to CPP, there's preprocessors for other languages as well. And in assignment 3, you used antenna in Java, right? Preprocessors are important in product line development because these usually include some facility for conditional compilation. If a condition is met, we include some code in the compiled product. If it's not, we remove that code, right? Conditional compilation is probably the most common mechanism for implementing variability in product lines in industrial practice, because a lot of product lines are based on C code or C++ code. So that's our prototypical example of tool-based, compile time, annotation-based variability. Antenna, as I said, is the one you used for Java code. So that's going to be our focus here. And it uses a set of comments you place in your code to note when to include or exclude code based on if statements and and expressions included with them. Generally, if a feature is included, it's defined as true, and if otherwise, it's not. And so we note if feature name to include code in the product, and if the code is not, if that feature has not been selected, then that code won't be included. Elif or else if can be added on to say, well, if we don't include this feature, but we do include this feature, maybe we now include this code. There's also just else, and we end this with an end if. Now, CPP will actually remove code entirely before compilation when it processes it. Antenna is a tool you invoke before compilation. So what it does is it comments out the code you've decided not to include. It doesn't actually remove it, but it comments it out so it's not included in your executable, which means the antenna can use the same files as input and output to cleanly transform the code. Right, so as a really quick example, we have two versions of the same class. In the first, we've selected features hello, beautiful, and world. In the second, we've selected features hello, wonderful, and world. Right, and so in the first one, we notice since we selected hello, this code is included. Since we selected beautiful, this is included. We selected world, so line 13 is included, but line 10 is not included because we did not select wonderful. In the second version, we did, so line 10 is included, but we did not select beautiful, so line 7 is now excluded. It's commented out with this little dash and the slash and an @ sign to indicate that the antenna removed this line, right? But this means we can pass this code through antenna, it'll comment out the code we don't want, and then we can invoke the compiler on that. Make sense? Any questions on this? There's a question asking if there's any special software we'll need for the exam. There's not. This is going to be similar to what you would have done in a hall exam in non-corona times, just as a take-home assignment. Instead, you're not going to need to use feature IDE. You're not going to need to use a SAT solver on this. It's just going to be more of answering different questions. Yeah, there's a note that they wish antenna is more Git friendly. That's completely fair. Antenna is not Git friendly. That's a perfectly valid thing to wish. And unfortunately, there's not a better one for Java really. Especially since CPP has the advantage of being generally part of your C compilation process in a lot of cases, so it can be more natively integrated. In Java, we don't have a native preprocessor tool. We just have these external ones. Yeah, it's definitely not very Git friendly. I've had that problem myself before. Now, in a parameter-based implementation, this is our simplest code-based implementation technique, right? Basically, we just use conditional statements like if statements and switch statements to alter the control flow of the program at runtime based on the feature selections we've made. So conditional statements are generally controlled by a set of configuration parameters passed either to a method or module directly or set as global variables in our system. Different parameter assignments then lead to many different versions, different configurations of a program when it's executed rather than at compile time. This is load or runtime based. Now, there's a lot of ways you can set configuration parameters. In general, we'd expect a Boolean parameter per feature, either set globally or at some appropriate level of scoping so that the program understands what the localized feature selection is. Often you use command line parameters or configuration files that are read in at startup, and then the values are stored as global variables, which can be referred to. This is an example of load time binding, right? If you take in command line parameters or you read a configuration file, you set those when the program starts and then run the program, right? And if you want a different configuration, you need to restart the program through the command line, having changed either the variables you're passing in or your configuration file, right? In other cases, though, this can be implemented at runtime, where users can change parameter either in a GUI by clicking different checkboxes, or as part of an API request, like as part of the body of your post request to a REST API. Sometimes with immediate effects during runtime binding, but other times, if load time binding, you might need to restart. Right. But parameters are a flexible approach. You're really just noting in your code, hey, check whether this variable is true or false. If it's true, that we've decided to include that feature. And so do the job this way versus some other way versus based on some other feature selection. This is pretty simple. It has its benefits and drawbacks, right? So we've got a graph example here of two configurable features, weighted and colored, implemented as global configuration parameters. Right, so at some point we've read in whether we're including these feature colored or feature weighted or not, and we've set those. So right now our default is true to colored and false to weighted, but when we read in our configuration file at load time, or if we take a command at runtime, we can go through and rewrite those. Within our code itself, we'll check these variables are stored in a separate class we're passing around, and we just check whether conf.weighted is true. If it is, then we've included that feature, and so we'll call this, we'll set the weight to be a new weight at initialization when the edge is added to the graph. If we're not using, so here when we pass into this version of add with a node, two nodes and the weight for the edge, if it's not weighted, we'll throw an exception because this particular method should only be called if we're using the weighted feature. Over here in the print, we'll check whether it's colored, and if so, we'll set a certain display color and print the ID. In our edge class, if it's colored, we'll set the display colored. If it's weighted, we'll print the weight out when we print the information on the edge. Right, so you can see here within the code that we'll check if a feature is being used, and then we'll call a certain code conditionally if it is or not. Pretty straightforward. Now, for both this and the preprocessor-based approach, These are simple, easy to understand approaches. The risk, though, is your code can get hard to read, and it can be hard to figure out where in the code that you refer to a particular feature. If you add a feature, you have to figure out the right place to add it. If you remove a feature, you have to make sure you carefully go through and remove every reference to it. And so this can get a little hard to keep track of over time. It's a little harder to make the code evolve cleanly when you're using these approaches, but they're also pretty easy to understand and pretty easy to use in practice as well. So there's ups and downs to it. Now, we spend a great deal of time talking about design patterns, and design patterns are a general concept, a way of taking our code and looking at different recipes for implementing different common code design practices. Right, so design patterns are descriptions of how objects collaborate within a program. They're essentially recipes for implementing certain kinds of behavior in a system. They're a classic object-oriented design technique, but they also have a major place here as one of the easiest ways to implement reusable assets in a seamless and extendable way to allow our system to evolve over time by slotting in new features and controlling how the system evolves. During the class on this, I highlighted 6 patterns. They're particularly suitable for product lines and other long-term evolving systems, right? The design patterns are one of our major means of language-based implementation. So as a quick reminder of the ones we talked about, the strategy pattern is a behavioral pattern where algorithms describe different behaviors. You take those, you implement them, and you make those algorithms interchangeable by ensuring they all offer the same interface. And so, for instance, we talked about this duck simulator. And once we implement this with a strategy pattern, we can swap different forms of flying behavior for others at runtime without needing to know the specifics of how they work. We just know that we can call all forms of flying in a universal manner and compose classes by attaching the right flying behavior to them. This even enables runtime variation, where we could change our feature for our duck at runtime, changing one flying behavior for another by plugging in the right class, right? So this pattern embodies a principle of object-oriented programming. Often we should favor composition of a class from different parts over direct inheritance of behavior, right? So we've got our duck. Our duck has flying and quacking behaviors, but some ducks quack and fly in different ways. So rather than inheriting how we fly from a parent class and then overriding it, we instead implement these behaviors once in their own classes, implementing a common interface. So we have a bunch of different ways the duck can fly, but they all implement a flying interface that offers this method called fly. So they're called in the same manner. A duck can quack in different ways, but they all get called in the same manner. They all get called by calling the quack method. So we can have different versions of this implemented with the same interface. And when we form our duck, we just point to the correct one that we want to use. So we can have all sorts of different ducks that can be reconfigured by changing their flying or quacking behaviors. Right? But this is this principle of composition, building a class from small independent blocks. It's something that we've talked about a lot with implementing product lines, right? We develop reusable assets and then merge them together to get the right version of our concrete product at the end. In these situations, inheritance can be useful to inherit certain behaviors, but only for the things that are truly shared across the product line, those commonalities, right? Composition is better for those aspects that vary and change over time. Our second pattern is what's called the factory pattern. The factory pattern gives us a way to encapsulate the instantiation of different concrete types, where we can reason in terms of 2 parallel class hierarchies, creators and products. Factories encapsulate object creation by letting subclasses decide which objects to create. And all the creators let us pass in options, use those to instantiate an object and pass the right version of that object back. The object we create, the product, can differ in terms of the methods they offer, but they all offer some common set of methods that we know about, right? So we have a client who's concerned with factories and products. For each product type we build, we have an interface that states operations that can be assumed of that kind of product. Those don't have to be the same operations, but rather we provide an interface for each type of products. So if we make pizza and sandwiches, we have an interface for pizza, we have an interface for sandwiches. All pizzas follow the same interface, all sandwiches follow the same interface. And then we have concrete product classes for each type that implement those methods of the appropriate interface. A factory gives us a way to create products of different types, and defines creation methods for each product type, be that a pizza or a sandwich or whatever we're building. So every factory is responsible for creating certain subsets of concrete products and links to the products it creates, and other factories handle other subsets of those products. The decorator pattern attaches additional responsibilities to an object dynamically. This is a nice flexible alternative to inheritance when you want to extend functionality without modifying the code. Decorators provide a flexible alternative to subclassing for extending our functionality. Decorators have the same supertype as the object they decorate. And given that use of polymorphism by inheriting from the same supertype, we can pass a decorated object in place of the original object. And that's a key point. Decorators can add their own behavior before or after invoking the behavior of the object they're wrapped around to perform a job. Right, so this lets us take code that's working, that's functional, that's just fine, and we want to leave it be, and extend it by building a class that wraps around existing functionality, adding on top of what's already been done with either new methods or new twists on methods that get called. So they'll invoke a method, perform its task, and then add things on top of that. Right? We can get functionality from the wrapped objects and perform any additional work that needs done without touching the code of the wrapped object. So what does this look like? Well, we've got two concepts called components, which get decorated, and decorators, which wrap around components. We deal with two levels of inheritance, right? So we have a base component that all concrete components inherit from. And these components are what we dynamically add behavior to. We have a base decorator that defines what all decorators must do, what methods they must offer. Since it inherits from a component, all decorators offer the methods that components do in addition to anything they add. Decorators contain an instance variable to store the object being decorated. And that's how we keep track of what's being wrapped. And we can infinitely keep wrapping, just maintaining a pointer to the next layer down until we reach the center. And decorators can also add new behavior by adding additional attributes and operations. New behavior is often added by doing computation before or after calling an existing method in the component, just like we illustrated in the previous class where we talked about this by talking about this coffee shop, where we have different coffees and then we add toppings to them like whipped cream or milk or sugar on top of that. The adapter pattern converts the interface of one class into the interface that the client expects instead. Adapters are basically a form of decorator. They let classes work together despite incompatible interfaces. So this pattern allows us to use a client with an incompatible interface by creating an adapter that does a conversion. Calling the methods of the adapter will in turn call methods of the class that the adapter is wrapped around, just with a different interface that we actually expect it to have. This lets us decouple a client from an implemented interface. So if that client ends up changing over time, the actor encapsulates that change. So the client code doesn't have to be modified. We just have to change the adapter class to continue working with this external system, this external code. It's a big deal for code reuse. It lets us build a system out of independent external code far more easily by wrapping it in the interfaces that are easier to work with, right? This looks pretty simple in our code. We have a client which sees only the target interface. The adapter is going to implement that target interface, so it implements the methods we expect. And then the adapter has a pointer to whatever it's wrapped around, its adaptee, and requests get delegated to the adaptee through the adapter. A similar idea is what's called the facade pattern. The facade pattern basically it creates a new class that exposes a few simple methods, and it lets us define an interface to a bunch of complicated low-level classes, right? So in the facade pattern, we create a class called the facade, which is an interface to a bunch of low-level classes. it calls on those classes to implement some simple high-level methods. So for instance, we might have an interface for starting and ending playback of a movie, and it talks to our Blu-ray player, to our sound amplifier, to our projectors, our screen, our lights, and our stereo to perform the task of playing a movie without you having to work with those individual objects on a more complex level. Right? The client works with the facade, it calls the facade in its simple methods instead of those classes, simplifying interactions. Those classes, however, are still accessible. We can still work with them if we want, if we have complex tasks we need to perform, but it gives us a simplified means of working with those classes as well to perform common tasks. As I said, the facade pattern provides a unified interface to a set of classes in a subsystem, and defines a higher level interface that makes that subsystem, the collected set of classes, easier to use. That's some feedback going on. There's no, could whoever that is mute, please? Hey, what we're doing here is we're just offering one more method of access, and that's a nice property of the facade pattern. We provide a simplified interface while still exposing the full functionality of the system to those who want it. You can even define multiple facades for the same subsystem, same collection of classes, to provide different situational functions, and this decouples the client from any one subsystem. If you add a new home theater component, you just need to change that facade. All right, whoever this is,
Suresh Vatru.
all right,
Irbeku.
there we go. Mute everyone. All right. And that decouples the client from any one subsystem. Any questions on any of this so far? All right. In that case, I'm going to go ahead and turn this over to Sam, who's going to go ahead and present the next part on modularity. And Sam, you're going to have to unmute if you haven't yet.
Okay, yeah, I'm ready to go to my part. I'm not sure how much time I should budget.
Just go ahead and continue. We've already said we're running long today and have not put an end time on this, so we'll just go as long as we need to finish everything. It's better than trying to rush too much.
Yeah, I mean, we'll try to keep it light.
Yeah.
Okay, this would summarize the first lecture on modularity. And its main reference was from feature-oriented software, chapter 3 and 4. And then whatever slides we reference from outside the papers. We'll introduce the concept related to modularity and talk about frameworks and APIs, and then some major drivers for design for modularity at the end of this. So in general, as it was mentioned in the design patterns, we are concerned about the issue of being able to map one-to-one as much as we can on features related to modules. As maybe in fancy world, each class represent, let's say, a feature, but usually that's not easily achieved. But we want really to develop a non-monolithic software, especially when you deal with complex situation, like in auto industry, and you want to be able to have your design modular and nice, your assets, your artifacts in your product line should be clearly traceable. You want to be able to improve the system traceability, testability, reusability, and deliverability, and maybe implementability. And we'll talk about this as we go. So we want these modules to be independent, easy interchangeable, and able to go back forth between the solution domain and the problem domain. Here we talked a little bit about the framework functions, and we identified the frameworks to be as a complex structure that could incorporate more than one class and enable software developers to produce a product of lines by just using the concept of a plugin without much modification on the software that you are using. Just a user could use runtime type of variability to use the plugin extension to develop functionalities and control features of the software. So how the we mentioned also that the frameworks work in a little bit different way than the software library functions in a term of that the framework calls for procedures and functions rather than doing it from the main program when you do like call a function in a library. So this is what we will call you, don't call us stuff. But I want to focus here on two issues that you need to be concerned about the exam is the white box framework and the black box framework concept in the sense that we talk about abstract class versus class that can be inherited. In the white white box frameworks, you know that you need to know something about the functions and the methods and the attributes of the class to be able to do sort of like extension of inheritance or extensibility activity. And in that sense, we say that the variability is implemented by you knowing something internal to the class or the framework. And that's where the name comes from, white box. So you as a developer need to understand the framework internals. And in that sense, white box is not really friendly to the idea of modularity. This is why it's been criticized and not widely used as in the black box. In the black box situation, which is the majority of what we see in software market, and here you separate the framework code and use extension points to expand and exercise your variability. And features are implemented by a separate plugin. And that's how you implement your features. So the interface is all what you need to know. You don't need to know anything about the implementation of the framework to exercise extensibility and variability. For example, we showed here when you are dealing with some software that is interfacing with either like, let's say a Windows ecosystem or a Mac OS, then you don't have to rewrite your software. You just need to implement an interface framework, we call it the black box, and it will go in between as a broker to implement your solution without having to develop different software for each operating system. To look at in more details here, we show you a concrete versus abstract class. Here you have a concrete class using white box. It's still reusable. You see the extensions here for the methods. As part of that, you need to know the internal of the framework to exercise extensibility. But in the situation of the black box, you use a sort of like aspects to extend. This would be like a broker in between. You call this external broker, and this is where you do the extensibility and change. And then it will bring back to the main framework whatever information and details. So the extensibility and variability is exercised here to handle these functions and procedures. This would lead us to talk about the concept of separation of concerns. And in this area, we need to make sure that the design and implementation of these artifacts are explicit in a sense that we separate the codes and the concerns for each class, preferably for each feature if we can. And we do that by implementing an external model, as it says, to do the variability and encapsulate this all whatever functionalities that is gonna be shared or supposed to be shared can be encapsulated and used across modules instead of having concerns across them. So you need to separate these concerns. So in this area, as I mentioned, we need features into distinct artifacts. When you have artifacts in your assets as to be used for product line, you want to make sure that there is no cross concerns and each asset or artifact is going to have its own independent code and variabilities. You don't need to change if you change one of your artifacts, like let's say a testing procedure or a class, it will not impact the other variabilities or assets that you have. Okay, in this, the issue of separation of concerns can be implemented through procedures. We call it injection. If you noticed here, there is a relation between a client class and a service class. And this relationship is called dependency. And this is a concern because these two modules are not decoupled and they are interconnected. We want to reduce this to something called soft dependency, which is not an issue when we deal with coupling. In this design, we have decoupled the two between the client class and the service by using what's so-called injector class. So this client would call the injector class requesting services, and this would be the adapter or the independent aspect that will implement the procedure and methods, and then will update the service interface. So there is no direct interconnection between the class, the client class, and the service class. In this way, we call it soft dependency through injection. And by the way, as I keep repeating, we put here the reference for you because if a question would come in that regard, you would need maybe more information, then you can refer to the reference as well. Cross-cutting concerns are also issues related to separation of concerns. There are certain methods that are difficult to isolate and implement them as independent because of their nature, like, for example, the testing procedures or maintenance procedures that are usually part of any class. And the way we implement them is to use aspect-oriented programming. An aspect-oriented programming that you create aspects, and these aspects are like the plugin. These aspects are the independent broker that will go in between, and where you can bring all these issues like security policies, synchronization, optimization, communication, integrity, and all these cross concerns can be implemented within the aspect. As you notice here from the diagram, you have these issues, the cross-cutting issues in these subsystems. And we implemented here a local aspect 1, aspect 2, aspect 3 to carry over the functionalities of these. And in this way, you remove them from these subsystems and replace them with the aspects to handle this issue of cross concerns or cross-cutting concerns. So this is how it's implemented. We can also talk in the same token about code tangling and scattering. It's a simple idea. We can see it from the diagram here. You have code tangling coexisting in the same class or package. As you see here, you have tracing, you have transactions, you have exceptions code mingled around in any class or any code. And these are, we call them tangled. They exist in all sort of classes. And this is not a good practice because this reduces modularity. And the way to implement it is to create an aspect. We call, for example, this is tracing aspects, and take all tangled code that relate to tracing and implement it in this aspect. Same way, you create this aspect for transactions and take all the codes from all the modules that relate to transactions, and you call this transaction aspect. And the same way here, all exception code, you handle it with the exception aspect. So in this way, aspect-oriented programming would help us clean up our classes and make them more reusable and easy to exercise variation on them using aspects. Information hiding is another issue that where you can implement them through encapsulation or different techniques in a way that we did in the black box framework, where we said we treat the whole collection of classes as a closed box. And in this way, users who implement or exercise these features or classes will not be able to tamper with the internals of the code and will be able to just create an external entity like an aspect or an adapter and then implement it within the code without causing coupling across the classes. The traceability concern is also has to do with the implementability concern. We will see how they are both issues. As you know, when you exercise your features in the variability model, feature model, the complexity, as Greg said, is MB complete. And when you deal with a number of features, 2 to the power F, you can understand when you have like 1,000 feature or something in that neighborhood, where this complexity will go. So in this complexity, doing traceability and mapping from the solution domain to the problem domain, from the problem domain to the solution domain, and back vice versa, you need to make sure that your design as modular, as capable of mapping and identifying your artifacts and taking them back as whether it's a code or testing or document, to make sure that it belongs to specific features. Because in the future, if you want to tamper with your feature model, you know what you are up to and what's going to be your expectation of a change. And you have seen this in some assignments that dealing with the code and which code belongs to which robot and which robot belongs to what code, and make sure that you are able to trace them and map them properly. Traceability, as you see in this feature model, from the color, the darker shade and the lighter shade, showing you that we can trace the feature model, feature by feature, to its implementation in a solution that use containers or virtual machines. In these virtual machines, you want to make sure what you implemented in terms of features and sub-features, and you'll be able to go back and forth between the virtualization containers that you implemented backward to your feature model. This is important because when you make any changes in your product line, you want to be able to trace it back to what you have implemented in your virtual machine as of functions and models. So this would solve the issue of traceability. And the issue of maintainability, it's not, I think the slide was missing. In implementability, usually when, let's say in auto industry, when they want to implement a new product line, they want to make sure that their stock of artifacts and assets are available and implementable. If they say we want this product line or a specific product even, they want to make sure that the amount of reusability of assets and artifacts justify the new line. Otherwise, if they have to create like more than half of the artifacts or create new features or redevelop their product line, then we have an issue of implementability. Implementability would have to do with not only the code, but the testing and the documentation and the stakeholders alignment and the whole organization alignment to make sure that you can deliver a product within the constraints of time and deadline. So this was also related to traceability, because if you work for a company and your boss asks you, can you deliver in 2 or 3 months? That's the way you're gonna do some traceability and implementability back and forth between your artifacts and your feature model. So this will conclude the first lecture on modularity. Let's move, I don't know how much time I have, but I will cover whatever. Mostly I focused on the second part of modularity on robotics architecture and how to make the design modular. And we mainly focused on autonomous design, autonomous agent, they call it. And the concept of autonomous robot is that we want to create an architecture that enable us to run a robot autonomously without a human intervention, to be able to make decisions, to be able to decide for itself any action based on the environment, sensing the environment around it. Not only that, we want to create a collaborative community of robots, like you see in any factory or in any situation. There is a vision for a future that we see, like they do research in Europe, I mentioned some about it here, that you need a group of robots as a community to collaborate. And also you have constraints. You want these robots to be decoupled, in a sense that if you remove one robot from the community is not affected, except you just subtract the function of that robot. You don't have to go and recode or do anything for other robots, which means the interaction mechanism of robots across each other is independent of the implementation of each individual robot. And this is a target by itself, like we did with the classes in the variability model of product line. The same issue is arriving. You can think of a robot as a product line and the group of robots as a collection of products in a software product line. And you want to be them decoupled, easy to change and do variability to create different community. If you need to build a robot for a production line, let's say auto, and change it to make it a production line for more different hardware equipments or different product line, then the changes will be specific to each robot, but not to change the whole community. And these are examples here of implementations of robots that can act autonomously in their environment. Some of them, they have interface, of course, of users, and that's okay. Here, for example, you look at the layered architecture in general of what we want from these robots architectures. Usually, of course, you have a user layer where you communicate with the robot. It's not necessarily to give commands or intelligence to the robot, but more of like viewing data, listening, or watching, or supervising what's happening. It's just a way to communicate and interface with the robot. Then you have the algorithm where all the intelligence is programmed and where all the sensing and planning and the actuation is taking place. Then you have a platform layer where you are actively making the decisions for the actions. We call it the actuators. And the last layer is a mechanical layer where you can actually do the electromechanical part of moving and the motors and all these things, the degree of freedom of the arms or whatever the robot is doing in its environment. In the simplest way, we talked about the three component model. This is sense, compute, and control. This is the beginning of robots. When they started building them, they envisioned that there will be a sensing for the environment, a planning, a brain, and then action. But this was like sequential, simplistic model. There is no feedback loops or any much intelligence there. As you see here, this just sense, think, act, sense, think, act, stuff like that. So the model came, that's called SPA, sense, plan, act. And the most of the activity and research was focused on the plan part, because this is where intelligence, at least early researchers thought that the intelligence of robot would be residing in the planning side. But nowadays, intelligence has moved to the actuation side because it interacts with the environment outside here and there. And you need to build some intelligence here to do advanced decisions for the planning part of the robot. Here, for example, just to set up some terminologies, when we talk about the SPA, what we mean, and when we talk about the product, the robotics paradigm, we define the relationship between the primitives. What are the primitives? These are the primitives of the robot: sense, plan, act. And when we say hierarchical primitive, because they are in order. And when we say purely deliberative system, we mean it just doesn't have feedback loops, and it is just doing what it says, sense, plan, act. But the story doesn't end there. We will talk more about having more sophisticated architecture to implement the autonomous robot. In the reactive paradigm here, you see that the issue of plan has moved to the area of sense and act. So, and here in the hybrid model, you just have mixed the pure deliberative with the reactive paradigm. We will look at this in the coming slide to show it in more detail. The plan part, as you see in the previous slides, the plan in blue here has been expanded, and there has been a proposal a long time ago to develop what's so-called subsumption architecture. In the subsumption architecture, they envisioned that the intelligence of the robot has to be divided into features, or let's say functions, or sub-intelligence. If you noticed here in the subsumption diagram, they call this level 0, level 1, level 2, level 3, level 4. And each higher level is superior over the lower level, in the sense that if attack wants to act on the robot, it will subsume the walk. It will nullify or stop the action of walk and do the attack. Same thing for the function, the intelligent function above it. It can subsume the layers before it. This is why you see this feedback here that will subsume, will like reset the action of the lower level till you get the highest command. If I can give you an example from a real organism intelligence. Let's take a fly, a small bug. In reality, the small bug, sometimes when it's flying, it is faced with different actions. Sometimes it sees food, and sometimes it sees a threat. Another predator want to attack. And here it provides priorities to its intelligent system how to act. We want robots to be like this fly. When it sees a need for multiple actions, how it will immediately in a short period of time, like in real time, act to see where the priority is, to get the food or expose yourself to danger, stuff like that. So you can build sophistication through the features here. These are, let's say, modules. You can put them into features and classes and decide what type of superiority they will have in your subsumption architecture. And this way, you will be able to do the planning part in more sophisticated way. The problem with this design is that these modules are not modular in a sense that they interfere. This module here interfere with the action or planning of the lower module. And in that sense, there is a coupling. And this coupling is a problem because if you want to remove one intelligence and add another intelligence, it might disrupt your whole subsumption architecture. And therefore, researchers think of a way to implement this subsumption without causing severe coupling or cross concerns within these modules. And you will see in the following, this is, for example, a diagram implementing one of the layers, like layer 0, how it makes a decision whether to move around when it hits, it collides with some object, what it does, and it keep running and moving in another direction. When it feels some force impacting on it, what it does. And this here, you define the behavior of this layer. I want to show that, here in the subsumption layer, we are converting these layers into features and implement these features independently. But the way to decouple these modules is shown in the following diagram, not this. I will come back to this later, but I want to show you this diagram. In this diagram, we have implemented the subsumption layers, as you see here, by using something called world state. World state is nothing but a shared memory. This memory is to design the next move and prioritize whether you're going to attack or move or do any other function based on the situation that you have sensed through the sensors. You see the input here from the sensors. So we implemented the world state to be able to make sure that all these are independent modules first, so we can interchange them or modify them or do variability design on them as to what we want this robot to do. And here the world state is receiving wish signals from each level to as what is the best move, the next move in the robot. I'll come back again to this, but let me go back to the slides that I skipped. Here, we are showing that we can decompose, as we said before, the robot to 3 layers, but different layers. We call it here the deliberative planning layer, which is the layer that has the subsumption. You have a sequencer that remember where the robot is and what's the environment around it and what was the last move. And here we have the reactive layer that does 2 things, the sensing world and then the action world. It does 2 of them, and it interfaces with the sequencer and the deliberator. So you need 3 things. You need to plan, you need to know the past or the current situation. So you need a sequencer, and this is a stateless, it's just sensing and acting based on the planning, the deliberative layer where it has the intelligence. This design show you here exactly what happens inside the subsumption layer and what signal it receives. It receives sensing from outside and a signal from the world state. You remember that world state was the memory in the bottom that keeps track of the state of the subsumption layers. So all this design is geared towards doing 2 things. We want to keep our subsumption layers modular, decoupled, easy to change, easy to modify, easy to add, so we can make more sophisticated robots. And the second thing, we want to make sure that whatever we do in this design will not affect the other features. So you can always gracefully add intelligence to this, and you will not have any problem with the sensing and the actuator, that they will always respond to whatever the subsumption layer give command to do next. Okay, so this was the final design that you receive 2 inputs. You have input from sensors and you have input from the world state, which keeps track of the current state. So based on what the robot sees in sensors and based on where it is and what's been doing, the decision will come through a wish signals here that go to the world of state, and some from the top layer, it will go to the actuator to give command for action, move, run away, or whatever you do. So this is basically the architecture of this robot to enact the design and develop it. Here is, I mentioned something about the SERA project, European grant, and I think this project is a collaboration between Sweden and some other entities. They have demonstrated their ability to create like 4 robots here, like you see in these 4 layers with different missions. They have programmed their robots in different subsumption layers of sophistication, of ability to do things. So they divided the functionalities and the duties and the purpose of these robots across like 4 robots and created a collaboration community of robots. And through each robot will have 3 layers. One we call it mission management and a change management control and components control layer. Through this design architecture, they were able to define a function for each robot. And then here is the central station to control the mission, design the mission. It's not to provide intelligence or give command to the robots what to do, but it's just to change the routine, change the software, change the monitor the robots, make sure they are doing what they are supposed to do. And there was a video, there is no time to show it, that shows the collaboration across these robots that are designed within 3 architecture. Here is the central station, and you do all the mission specification and supervision, mission management layer and control layer. It explains what they are doing. So this would lead us to another topic, which is the feature-oriented programming. And in that sense, we want our programming practices now to be based on features rather than classes. And in a sense, of course, we said in the ideal situation, you either have features that represent a class, or multi-class represent a feature, and vice versa. We talked before about feature traceability and feature separation and collaboration and roles and feature modularity. These are the things that we covered in this lecture. We talked about feature traceability before between the problem domain and solution domain, and we made sure that if we can do one-to-one mapping. And we talked about the traceability from your problem domain. You have feature model. You want to go back to your artifacts or assets and be able to map them, if not one-to-one, at least to have a clear mapping. This would help you a lot in doing implementability. We mentioned about design for implementability. And it's very close to the concept of traceability, because here you just want to make sure you have enough resources, enough assets to implement a new feature or a product line or a specific product by tracing your feature model with what you have and how much you need to do in terms of modification, variability, or redesigning of new features. In this area, it shows you the relationship between class and features. For example, you see here on the left that we have these features from the directed diagram. You have search, directed, weighted, and color. And as you see, the fulfillment of each feature has gone, of course, we said in the ideal way that each feature is represented by class, but this is not the reality. Usually, a feature will be represented by instance from different classes. This does not violate the principle of modularity, but at least it shows you the mapping clearly that to implement this feature, you need a certain methods or procedures from graph, and you need maybe certain methods and attributes from node. And this way, you will be able to implement all these features. And this is how you do implementability. You make sure that all these features that you created are available within your assets. Maybe they are not straight one-to-one, but you can really use certain classes, functions, and implement this feature as you wish. Here it shows it very clear we call it feature refinement. If you cannot implement a single feature as a cross reference from different classes, you can also divide your feature. So let's say R1, R2, R3 combined can represent one feature. So we call it refinement. And in the same way I showed you before that each feature was represented in different classes, the same way here we see the refinement can be represented into different classes, and combined, these refinements combined, we call them layers, can be representing a feature. So there is a flexibility here in developing classes and refinements, layers of refinements to implement the features. This would quickly conclude the modularity. I did it fast, but I want to emphasize before I go to the next one, that in terms of the exam, if we have like multiple choices, it will be basically on this material that we just covered today, but maybe expanded through the references. If you don't find the answer or the clue for the answer within the slides, please refer to the reference material, the papers, whatever it is. You will find a trace of a solution, a trace of ideas that will help you solve the exam. So in that sense,
question in the chat before you go on.
Yes, sure.
So there's a student asking specifically for some more clarification on the robotics modular architecture and what the main takeaways of that are, because it feels disconnected from the other material that you've been covering.
Which one in particular? This one or the previous one? Subsumption layers or the Sierra project?
I mean, check the chat, but I think in general, the examples on the robotics modular architecture.
Yes, as I said, I summarized that by saying that the purpose of all this design is to be able to create the intelligence in the subsumption layer, whereby we can implement it into independent features, make sure that they are decoupled. Because previous designs were like hardwired. Everything is so complex, and if you want to change the functionality of the robot or change the codes, like you did in the assignment, we don't want, when you change a code of one robot, for example, it affects the other robots that are collaborating in the product line. Or at the same robot, we have so many capabilities within the single robot. You don't want to be able to, you want to be able to make variability in this design of the single robot without interfering across the classes or the features. We want to reduce the interaction of features and make sure that we are capable of doing more sophistication in the terms of planning for the robot without disturbing the other features in a way that is easy to add and remove. It's like a product line. Think of a robot as a product line that you can add capabilities to it by adding features and subtract by removing features. That's in a high level. But if the question is specific, for example, to look how this works, we can spend more time on this. But I'm telling you, your responsibility as far as the exam goes is to understand the motivation behind the design and why we do what we do. We're not going to go into killing details and tell you what is the purpose of, let's say, the wish state signal that goes into the world state in the subsumption design. No, that's not the purpose. The purpose of the exam to ensure you understand the concept. And once you give us the signal, then you are okay. So please, we are not trying really to make it complex on you, but rather examine your conceptual understanding. I hope this answered the question, but if you can be more specific, I'm willing to elaborate further. How much time do we have?
Why don't you just give some of the highlights for the next part, just to make sure we have some time to still cover testing?
Okay, the other part is not going to be long, really. I can maybe finish it in 10 minutes.
Sure.
Because I just want to focus on what's important. And on this, I have removed lots of slides from this. The first thing about the agile product line engineering, the motivation, why we want to convert or migrate the practices of large companies that build very complex software like Volvo and GM and Lockheed Martin and Boeing and all these companies that have millions of codes of software. And they are not really yet agile, because there is a common understanding in the software development community that agile is something you can implement in a small software, in a small projects. But when you have legacy software that goes into millions and millions of code, and it's already there, and it's been developed over tens of years, then the movement from, let's say, waterfall design or traditional design that goes into collecting requirements, building software and testing software and doing that, to small cycles of agile is really difficult when you have a product line. So the research here that we present is focused on this problem. Yes, there is a challenge when you have a product line to make it agile because of issues related to the history of the industry, issues related to the complexity of what you're dealing with, and issues related of the teams who are developing the software. It's been difficult for big companies to create smaller teams to develop software. Because when you develop software, you involve so many departments, so many units, so many suppliers, so many vendors. To put them in a teams of 7 or 9, like Scrum says, or any procedure, Kanban, or whatever it is difficult. Therefore, we present here a way or a methodology that companies have adopted, like GM and Lockheed Martin and others. I'm sure Volvo is also involved in this agile practice because it's more productive for them. It's more lightweight, that they can move quickly and respond to the market. Example, I can give you the auto industry. The problem time is limited. In auto industry, it used to take 4 to 5 years to develop a new car, totally new product. Nowadays, the industry is pushing them to be able to develop a car in 2 years. That means you have to develop maybe a new class of software, especially in electric cars, let's say, within 2 years, like what Volkswagen is doing, developing a complete electric car within 2 years. That means all software has to be started from maybe some very early point and develop it complete. So the researchers are calling for an agile process to develop software in a very short period and very productive, continuous delivery, continuous testing in small teams, and be able to deliver it tested and ready to deploy. That's the motivation behind the whole thing. So we call this Apple Agile Product Line Engineering, and it is, we talk about the framework that we're gonna introduce in the next 10 minutes or so. This background of thing you maybe all know about Scrum. Usually it's more used by these companies, especially the one I quote. And in particular, Scrum Pan is used by like GM. It's a combination between Scrum and Kanban, the Japanese process of quality development and software development as well. So what we are saying here simply, this is another motivation curve. It shows you that using the old way of developing software, that like the waterfall way, how it will do exponential in terms of cost when it comes to testing and coding at the end. Maybe it's easy to go collect the requirement at one time and ask your engineers start developing things. Great. You see it faster than doing agile thing. But the penalty, you pay it heavily when you start coming here for debugging and fixation and variability and changing to different versions. The cost will be skyrocketing here, and this is why the argument is for agile process would be cheaper. Second argument is about the size of the project. I'm talking about companies that have projects in the code of 10 million lines and above. And as you see from the industry history and profile, small projects have less failure because they are small, simple. It's easy to control. But in large projects, the failure is like 38%. Why? Because there are lots of issues interacting, lots of moving parts, lots of testing, lots of debugging, and the failure rate is higher and the cost is higher. And that is a case for motivating Agile in large projects to reduce this amount of failure and reduce the unpredictable results of this development. In particular, I was talking about Agile framework for product line engineering. And the reference, you see it down here, it talks about Agile FPL. And we talked about the implementation using Scrum Pan and goal-oriented engineering. They call it here goal-oriented requirement engineering. Just the code is GORE. These two principles, using the GORE and implementing the Scrum Pan of Agile software development, are used in this framework as a proposal. And I elaborated more in this process of how you take a product line engineering and convert it to Agile to be within the scope of Scrum Pan practice. So I give an example here of how you are moving from the domain engineering level, and I showed about here 16 steps of what they have done to comply with the requirement of short Scrum cycles to produce not only software artifacts at the end, but I'm talking here about domain engineering. Even when you do feature modeling, even when you do creating a new feature, you still can use the same principles of Agile to come up with the feature model, to come up with domain design, to come up with feature backlog. This is features backlog. You treat it like we treated any story backlog or use case backlog. So for the sake of time, it's self-explanatory here, but as far as your exam, all what I want you to understand these 16 steps of what is happening here, and they are self-explanatory as you see them from the diagram where it start with software vendors here, meeting, and they develop a business strategy, and then they go to the design requirement engineering in this area, and they go into a back loop and strategy pull, strategy push, till they come with something called domain design. And once you have the domain design, you can do the feature push. Then they start pushing feature after feature. If you have the feature in your assets, it's great. If you don't have it, you develop it. And then here you have your stack of features to be implemented. And then you push the features here to another team that will put it and prioritize it into story in progress. So they take the features, it could be implemented in different stories, and put them in a stack here for the next team down in the application domain to take it. So you can see it here from the solution domain. We are still in domain engineering. This is the solution side where you're gonna create the artifacts. So you start developing them here. They come back as stories, like you saw in the previous diagram, and they go through the process of testing and development, and they ended where? In the common assets. This is domain engineering in its finest. At the end, all what you need is this: your common assets of artifacts that are ready to be used to develop new products. If they have issues, they send it back. That's how it works. And they have the retrospective meetings, they have all the things like you learned in Agile process. And at the end, you have your assets here preserved. Also, we moved to the application domain. We see how they use this stack of backlog. There are two backlogs here, SOF and BOF. SOF is selection of features. And here you have DOF, which is definition of features. SOF are features ready to implement. They are ready, part of your assets. But DOF are features that need to be implemented. They are not implemented. So they separate them. Part goes to your assets and parts go to the development team. Here in the last diagram, you see where the solution for applications. Here they are pushing complete application. as you see here at the end, you have application I, or application 1 or 2 or 3. It comes here to them to the sprint meeting. It goes into sprint backlog, like you see in a single product. And they have and at the end, they produce the product from the features that they got. So this is showing you a complete implementation cycle, how it is done in the industry using the Agile FPL. And the Agile FPL is giving you a way to implement the principles and the practices of Scrum Pan into a product line development. That's the general summary of that. As far as the exam is concerned, I just want you to understand how this is different than the standard procedure that used in product line development. If you want it to be agile, if you want it to be Scrum Pan, if you want it to be following the Scrum procedures of agile, this is how they do it. And there might be some questions related to this. It will not be, most likely, it will not be a multiple choice. It will be just an open-ended essay or question about this process. So please pay special attention to this framework. There is a reference there. You can read the whole thing from the reference if you want more details, and you'll be fine. You see the reference here in this page 68. This is what I want to say about the Agile framework as we use it. I also mentioned quickly here, I don't want to talk much about Lockheed Martin, but I mentioned that they have an issue of having big projects, big software running their systems. And they have 200 engineers like working on one product line, 800 engineering in different working on a complete product line. And in one system, maybe 200 engineers are involved. So what they did really, they divide their teams into smaller cycles from 4 months to 4 weeks or 2 weeks. And the teams from 200, they made teams of 7 and 8 engineers. It was a big challenge, but they went through it and it's working and they are happy with it. That's as far as Lockheed Martin. But in General Motors, the story goes into, I'm focusing here on automation tools. They used Bilever from Gears product. It's called Gears from Bilever. And I showed some examples of how they used Gears. I will just focus on the diagrams here. And the General Motors, they created something called the superset. You can call it their asset, their artifacts. So they have all of these there in their assets set. And each asset has something called the gear, which is the variability point. The gear means based on the feature catalog, this is the feature model. Based on the feature catalog, if there is any change, any variability they want to practice on their feature or their artifacts or assets, let's say this is a test code, they want to change it a little bit, then they do here the modification. As you see here, the gear changing the assets variability before they push it to the configuration in the product development. Here you have something called feature bill. The feature bill is the bill of features in factories. What is going to be included in the product? So here they decide from their feature model what features would be selected for a specific artifacts, and they go to the configuration to produce the product. This is just the big general picture of how they do it at General Motors. Of course, all of this process is automated using Gears. And we mentioned some information about how Gears as an automation tool like Feature ID or a pure variant are helping them defining these things. They have feature declaration, feature profile, feature variation points, and defining the assets. All of this is done inside Gears. Here is more close example of how they are doing it when they produce artifacts for their products. And here, for example, this person here on the left, indicated by the gear symbol, is practicing the variation points. As I told you, the assets have variation points. and they change these variations. And then here you have bill of features is decided by this engineer, development engineer, to provide the feature profile for each product. And here they do the variability, the variation of their features or assets. It goes into the configuration model, which is called gears, and produce artifacts here or final products. So this is just showing you this slide focus on using gears in combination with other tools, because General Motors is dealing with like thousands and thousands of subcontractors, and they are their vendors. They provide them with systems, with products, with software. No auto industry works by itself. So Gears has to cater to that. If they are one of their vendors is not using Gears, let's say they use feature ID or pure variant, they developed here what's so-called the bridge. As you see here, these are the bridges here are implemented at the edge, at the edge of Gears. It enables them to interface with their vendors. These are their vendors that are supplying them with external products and services. They come automatically, and they have developed through their bridge a plugin that will enable them to read automatically their design. Example, if they are getting a feature model, let's say a software coming from a company that's doing autopilot or doing climate control in their car, and it's developed by a third party, it will come here and Gears will take it, translate it into GM system, so that Gears can use it without a human intervention and include it in their design and developing the product line. So this way, General Motors does not have to go to each vendor and tell them, oh, by the way, we use Gears, we have to have this requirement and specification. No, they tell them, do it in any tool you want. We'll just develop the plug and we will take it, we translate it, and we use it as it is. Because these companies keep developing different versions, different styles, and they don't want to do anything crazy by redesigning or anything to they can take anything from UML, from any types. They use, by the way, a tool from IBM. It's called Doors. Doors is helping them collecting the requirements and translate it to a language that GM will understand. Requirement is very important in this ecosystem. So this is roughly showing you the roles in GM, and says this is the most important engineer here in the process. It's a product line integration engineer that does create the bill of features. If you remember, the bill of features is the one that does the instantiation of the feature model, deciding what features go in, what features need to be modified. So it produces the feature, the bill of features, rather than the bill of material, and tell them, okay, in this car, we need this package, go ahead and develop it. And it shows you the role of each of these in the model. So this is roughly what happens in GM. I think this was the last thing. If there are any questions, we can take it from there. Okay, let's see. Do we have any question?
Doesn't look like it.
Okay. This will conclude my part. Oh my God, we are 48. Okay. Well, I'll be around. I mean, if anybody has a question or anything.
Great. We have one more unit to get through. I definitely applaud the 25 of you or so who are left still watching. What I'm going to do now, we're just going to take a 5-minute break, come back at 53 after, and then we'll go through the last unit of this, but give you 5 minutes to go grab a coffee, use the bathroom, whatever you need to do. All right, let us get back into it. And like I said, just one more set of lectures left, and then you can finally go to sleep for the day. So we can break testing into a set of independent stages that we stagger throughout the development process. And these stages are largely built around different levels of granularity within the system under test. If we look at the system from the outside, it might look a bit like the box here, right? We don't know what's going on inside, but it's got some interfaces, maybe a GUI, maybe an API, maybe some kind of command line interface. However, there's also a lot going on inside, of course. The system as a whole tends to be architected, as we saw, as a set of larger independent subsystems which communicate with each other through their own interfaces, right? And the subsystems communicate with each other and with external systems as well. Then within those, we have a lot of individual standalone units or classes all working together to produce the functionality that's offered by that subsystem by calling methods in the other classes when needed, with methods forming another kind of interface. And we need to test at all those levels, class or unit, subsystems, and the system as a whole. So broadly then, when we talk about testing, we talk about testing either at the unit or the system level, with a couple of distinct types of testing in there. And then we have other concepts like acceptance testing and alpha and beta testing, which are we're not really dealing with here, right? In unit testing, we want to know if the methods of the class of an individual class work in isolation. It's where we spend most of our testing time. We take a small piece of the system, what we call a unit, but really this is the smallest independent chunk of the system we can work with, usually one class at a time, or a small cluster of classes. And we test those in isolation from the rest of the system. We take a class and we come up with tests for each of its methods. We try and isolate these as much as possible, even faking the results passed from pieces of the system that we haven't tested already. And then we move up the ladder to what we collectively call system testing, which encompasses three things. What we call subsystem integration testing, where we bring the units together and it tests the individual subsystems on their own and tests the integration of the classes together within those subsystems. Right, where classes call other classes and see if they can work together without breaking anything. Even if we've tested the individual units, faults can emerge from their combination. So we integrate the units together and we test that combination and whether the subsystem as a whole can perform the functions that we stated in our requirements, right? And when we bring those together and test the integration of those subsystems to form the system as a whole, and we can test the system then through its high-level interfaces to test the integration of the combined system and ensure there aren't any integration errors and that the product as a whole meets the requirements. This is what we call system integration testing. The third element is what we usually call UI testing or end-to-end testing, where we test from the direct perspective of a user, generally through a graphical interface. System integration testing and UI testing tend to have a blurry line between them, right? And more come down to whether tests are run through a graphical interface or a program level interface like a REST API or through the command line. Creating system level tests is a 5-stage process, where first we need to figure out what the independently testable functionality of the system or subsystem is that we're testing. What are the actions we can perform by working with it? If we are working through a defined interface, what are the actions defined by that interface that we can perform in isolation from the other functionality accessible through that interface? Basically, how can we prod the system and make it do something? For each of those high-level functions, we need to identify the set of choices we control when we're testing. What is it that, what kind of input do we provide when we use this feature? Now that can be the actual input parameters, like the information we pass into this function to make it act, but also other choices you control when you're testing. In a product line, this includes the set of features that you would choose for each variation point. Right? So what are the variation points that we make a choice for when we test this particular function of our software? It also includes other environmental factors, your database connection or the contents of the database that you interface with, right? Now, the next step then, for each of those choices, what kind of input can we provide to it, right? not just if it's an integer, not just 1, 2, 3, 4, 5, etc. to the max integer, but what kind of input can we provide to it? How can we carve up the input space for each of those choices into a reasonably small set of choices? Now, for a product line and its features, that's less difficult, right? That's if we have a variation point, what are the options we choose for it? Like if we can choose between different database types, what kind of databases can we pick for that variation point? That's much harder when we're talking about an open-ended input, like a number, like a string, where you could have a potentially infinite number of options, and you need to carve those up based on the different outcomes that they can trigger. And this is going to give you what we call these test case specifications. Test case specifications are abstract recipes for test cases. They combine one choice for each of those or one representative value for each of those choices. You combine those, and those form these abstract tests. Now, these will say, choose this kind of value, choose this kind of value for choice B, choose this kind of value for choice C. And from there, you can create one or more concrete test cases where you fill in a specific value rather than the abstract representative value, right? Now, this process typically leaves you with the Cartesian product of all the choices and representative values you can make. So this can lead to hundreds of thousands, if not millions, of test specifications. And you're never going to write that many test cases. You're not going to write more than a couple dozen at most test cases for any one function in most cases, right? Not hundreds, not thousands of test cases. And so which test cases are important then? All right, so what do I mean by generate a test specification? I mean create the test, an abstract test case. So if we go back to this process, we have a set of choices we make when we're testing, when we're creating a test case. And for each choice, we have a set of values, right? So one test specification is just selecting one value for each choice. Does that clear up your question? Right. Now, of course, you can imagine then if you have 5 choices and 6 values for each, right? So that's going to be, the number of choices you can make is you choose one for each of those, and that's going to create a huge number of possible test specifications. And so we need to prune this down, right? You're not going to try all of those. What we want to know instead is what are the interesting test cases, right? And so we looked at 2 processes for how you can choose these, especially aimed at feature-rich systems to capture, rather than trying to capture every possible interaction of choice for every variation point. What are the interesting feature combinations, right, that we should focus on when we're testing? And we looked at 2 processes here. What's called category partition testing, where we use a series of constraints to filter our choices down, and combinatorial interaction testing, where we try and capture all 2-way combinations of feature interactions rather than all n-way feature combinations. And let's look at both of those quickly. Okay. So in the category partition method, we go through and we generate these, where we create this set of test specification, these test recipes, right? So for a particular feature of our or function of our software, we look and we identify what we control when we test. Those are those choices. Those are the input parameters, environmental factors, and feature selections we make when we're testing this particular function. For each of those choices, we identify the set of representative values, right? The different options that can cause different outcomes when we test. And then the new part of this process in category partition method is that we lay a set of constraints, 3 types of constraints called if constraints, error constraints, and single constraints. And what these do is these help filter down from trying to run the full set of test specifications down to a more reasonable set that captures the important scenarios that we can cover. This concept of adding constraints lets you estimate the number of test cases that you'll need. And more importantly, it means you can apply more constraints to further limit that set if you find it's still too large of a set, right? This lets you determine the number of test cases you'll need to create before spending human effort creating them. And that's a powerful concept. If you end up with too many test cases you need to create, well, maybe there's more constraints that would make sense to apply. and which is a better approach than just trying to build an exhaustive set of test cases and realizing you've run out of time, right? So there's three types of constraints we can define to reduce the number of pairings. The first are these if constraints. And what these do is they let us say, well, if we choose a value for one of these choices, then we are going to limit what values we can choose for other choices, right? So if X is true, we use value Y for this particular choice that we're making. The second are these error constraints. So when we have a particular choice of representative value that, regardless of what you combine it with, is going to cause an erroneous output for this function, and it's going to cause something other than the normal happy execution path, well, then we don't need to try every combination of value for other parameters with that particular value. We just want one test case with that value to show that we get the error that we expect, then that our error handling code works as we would expect, and we filter out every other combination then because those are redundant. Then we have single. Single is identical in functionality to the error case, but it's a more general purpose idea. What we're doing with a single constraint is we're singling out a value and saying this is a special value, but it should give us the normal happy path through the function. This value is special or unusual in some way, but it should still give us the good normal outcome. We just want to try it once to be sure it works and doesn't cause anything strange to happen. But we don't need every combination of values for the other choices in combination with this one special one. We just want to try it once in a test case. We don't care what we pair it with. Just try it once and make sure it works and move on. Right, so to give a simple example, we have a substring function. It takes in a string and an index, and it returns everything from the beginning of the string to this index. Now, for this, this particular high-level functionality, this substring functionality, we identify three choices when we're testing. We have the length of the string that we control, we have the contents of the string, and we have the value of the index we pass in, right? So three things. Now, for each of those, we're going to identify these representative values. These are important values or ranges of values that lead to particular outcomes. So for the index, right, well, how the functionality works is the index gives us everything from 0 to whatever the index is from the string. And so we want to try a negative value, which should give us an error. We want to try a 0 value, something greater than 0, and maybe 1 because that's a boundary condition. For the string, we control both its length and its context, and both have an important relationship to how our test case works, right? So we might try a length 0, a string of length 1, a string of length 2 or more. That's our normal string, but a single character one to make sure that works, and something that's 0 to make sure we get the right outcome. And then the contents of the string, well, maybe it contains letters and numbers, maybe it contains special characters, or maybe we try a blank string. Now, of course, looking at this, not all these make sense in combination with each other. And so we can use these constraints to limit the combinations we try, right? So a test case specification would be one selection from each of these choices. So length equals 0, contains letters and numbers, and value less than 0 would be one specification. The total set would be 3 times 3 times 4, right? So 9 times 4 is, 36. Yeah, that should not have taken as long as it did, right? So we won't write 36 test cases. Let's constrain this down a little bit. So first we have these if constraints. And what we do is we define a property. We say that if length equals 0, then this property called 0len is true. Now, down here we'll say that we will only use an empty string if we selected length of 0 for this choice. And for these other two, we will only use either of these if this is false. If the length is not 0, we'll only use these. Okay, so this is now going to reduce the number of test specifications we create. We won't create any with the empty selection with length 1 here, or length greater than or equal to 2 here, right? Because that's not an empty string. It doesn't make sense. And so we use this constraint to denote that, right? Error cases are cases where regardless of what we choose for string length and string contents, An index less than 0 is a problem, right? That's not our normal happy execution. That should instead return some kind of error saying, look, you can't give me a negative index to a substring function. A string can't have a negative length to it, right? So we mark this. So that way we don't try value less than 0 with every one of these 6 options. We just do one test case where we can choose anything for these. It doesn't really matter, right? But we just create one test case with value less than 0 to make sure it works. Then we have the single constraint, which is, in this case, for a string of special characters, that should be fine. That shouldn't go wrong. It should work just fine here. But we're going to try it once just to make sure it works. Make sense? Any questions here? All right. Let's go on then to combinatorial interaction testing, right? This approach is similarly is a way to reduce the number of test case specifications that we're going to create test cases for, right? But sometimes it doesn't make sense to come up with those kind of constraints like we saw for the substring function. So here we have a system that controls the display of our website, our product line. We have different options for this particular website that we can choose. For instance, we can have a different bandwidth modes, so desktop site versus a mobile site versus a text-only site. We can display in 4 different languages. We can display in 3 different font styles. We can display at different screen sizes, a phone, tablet, and full size. And we can have different advertising modes from no advertising to general to minimum and targeted. Right, so now in this case, this would get creating all test specifications will require 432. So 3 times 4 times 3 times 4 times 3, 432. And there's not really many natural constraints here. So the question is, what's important to cover? Well, combinatorial interaction testing can help with this. And is one of the more common approaches for deciding how to test product lines. It really maps naturally to that format. So when is it reasonable to expect some potential interaction between features, but covering all the combinations isn't practical? One alternative is to cover all k-way combinations up to some limit of what we want to examine. So usually this is pairs or triples. So all pairwise or 3-way combinations between features. How much does that generating possible pairs of values save and comparing with coming up with all combinations? Well, it's quite a lot as it turns out. If we need to create all test specifications, the number we create grows exponentially with the number of choices. It only grows logarithmically if we're covering all pairs of values instead. So in the example on the last slide, we need 432 test cases to try all feature interactions. But if we only care about 2-way feature interactions, right, interactions between pairs of features, we can cover this in the total of 16 test cases. So if we look at our website display, where we had 5 different choices and a set of representative values for each of those. We'll start with, if we want to come up with all pairwise combinations here, what this process does is it starts with 2 of those choices. We start with the 2 choices that have the most options. So 2 of those have 4. Advertising, we have no advertising, targeted advertising, general advertising, and minimal advertising. For language, we have English, French, German, and Swedish. And so what we want to do first is come up with all combinations of those 2. We'll need 16 test cases, 4 times 4, to try all combinations of those 2 features, right? Here's English with no advertising, English with targeted, English with general, and so on. French with none, French with targeted, French with general, French with minimal, German, and Swedish, right? Now then, rather than trying to capture all possible combinations between all these, now what we'll do is we'll add a 3rd variable. And what we'll try and do is pick values for that 3rd one to match with language and advertising. So we cover all pairs of this 3rd one with language and with advertising. So we can bring that in. And the next one we'll bring in is our bandwidth mode. There's 3 values: desktop site, mobile site, and text only. And then we'll try and choose values of that so we capture all combinations of bandwidth mode and language and all combinations of bandwidth mode and advertising. And we can do this pretty easily within that 16. So here's desktop site with English, desktop site with French, desktop site with German, desktop site with Swedish, desktop site with no advertising, desktop site with targeted, desktop site with general, desktop site with minimal, right? And with all of these, we can do the same thing. So now in our 16 test cases, now we've covered all interactions between pick two of these three variables. Now we'll add the fourth, we'll add in the fonts. And here again, as we fill these in, we can pick a value of fonts to match, to try and cover all combinations of fonts with language, fonts with advertising, fonts with bandwidth mode. So here's standard in English, here's standard in French, standard in German, standard in Swedish, standard with no advertising, standard with general advertising, standard with minimal, standard with targeted, right? And again, we choose these carefully so that without adding any additional test cases, we've now again covered all two-way interactions between all four of these parameters. And as we do so, we sometimes have to go back and then fill in ones on this one that we had previously indicated as we don't care what its value is. And now we can add in screen size. And when we add in screen size, we again try to pick our values so that we get all pairs of these, of screen size and language, screen size and advertising, screen size and bandwidth mode, and screen size and fonts. Does this make sense? What this means is that in 16 test cases instead of 432, we capture all interactions between pairs of these choices, right? Of language and advertising, language and bandwidth mode, language and fonts, language and screen size, and so on. Now, this might mean we miss some higher order interactions, cases where a particular combination of 4 or 5 features is going to be a problem, but most feature interaction problems are really between pairs of features. And so this will capture most of the feature interaction errors in any of our concrete products that happen when we integrate particular features from our product line. Any questions on this? All right, then we have the very last topic we talked about, which was automated test generation, right? And test creation is a hard process. It requires a lot of manual effort, especially if we want to achieve any sort of meaningful volume when we test. And so we can release some of that cost by doing things like automating the creation of test input. We talked about test creation as a search process, and this is the idea behind tools like fuzzing tools. Fuzzing tools are used quite a lot in industry right now in order to identify crash errors as well as security vulnerabilities in software. And it does so by generating test cases intended to cover the code base of the software as a search process. So what we can do is we can think about testing as a search problem. And the common thread is that we have some purpose in testing, some kind of goal we have in mind. Maybe we want to make a program crash. Maybe we want to cover all two-way interactions. Maybe we want to achieve coverage over the code base. Whatever we want to do when we create tests. Well, then out of the massive space of input, then you're searching for the particular test suite that achieves that goal. If that goal was measurable, then we're in good shape. So if you have a goal in mind, and if we can judge whether or not we've achieved that goal, then you have a search problem. Of all the near infinite space of inputs, we want the set that meets that goal. Then we can have an algorithm sample test inputs from the space of all possible input in an attempt to optimize that goal, right? Now, the ultimate goal of testing is usually to find all faults, and that's not something we can check attainment of because we don't know ahead of time what those faults are. But we've invented all sorts of practices and all sorts of measurements as approximations of the idea of fault finding effectiveness. If you do A, B, and C, then you're more likely to find a fault than if you didn't do that. And the majority of those can be measured. We can either see if those are Boolean properties, that this property is satisfied or not. We can, some goals we can measure, like code coverage. We've covered 75% of the code base. Others, we can just count the number of crashes or exception we've thrown, for example. But if any goal can be measured, then that search can be automated. And the rough idea of a search process is to guess, check whether our guesses were right, whether we met our goals, and if they didn't, see if we can learn something from that. Gather some information to alter the test cases that we're creating over time, avoiding bad solutions, and converging closer and closer to finding the test cases that we need, right? So that's our equation for success in search-based test generation. Testing has one or more goals, such as executing certain code elements, driving the system to throw exceptions, or detecting planted faults. This process should yield test suites that meet those goals. The meta heuristic, the algorithm that we use to choose input and reformulate that population, and the fitness functions, numeric scoring functions, combine to yield those results. The algorithm is responsible for population evolution as guided by the fitness functions. Those functions offer strategies that shape test suites, ideally in a way that brings us closer to our goals. The meta heuristic formulates solutions and then uses those fitness scores to decide which solutions to promote and how to reformulate the population using elements of the good solutions and learning how to avoid bad solutions, right? This process is used in fuzzing daily by companies like Google and Facebook and Microsoft to identify bugs and security vulnerabilities in the products you use every day. And this is a good way to automate a lot of things in testing, right? There are a lot of different topics, from test case generation to creating these combinations of test cases for combinatorial interaction testing, to even creating patches for common software bugs that follow the idea of making guesses, learning from those guesses, and reformulating to try and optimize a measurable goal. Okay, are there any more questions? I know this has run a really long time. I absolutely thank you for your patience. If you have any other questions, feel free to let us know either now or through email on Canvas, leading up through the holidays and leading up to the individual assignment. At some point, we'll try and put a few sample questions online. Maybe ideally at least by January 1st, if not sooner. We'll try and get some things up. But let us know if you have any questions in the meantime. Keep working on those assignments. Assignment 4 is due Sunday. Assignment 5 is due January 10th. But that's the last lecture. Thank you all for making this a great course. I hope you've learned something. Thank you for having patience with us throughout this. And have a great holiday. Stay safe. We'll see you afterwards. And just again, let us know if you have any questions.
Men det finns, ja, det finns lusebullar i. Ska vi följa?